Welcome back to Honors Calculus. In this video, we're going to be looking at properties of limits. Now that we understand how limits work, our goal is to never have to do that again. If we can prove some general rules about how limits work, that we can evaluate limits at certain conditions and everything behaves normally, then we never have to think about an epsilon or a delta again as we talk about limits. And if there is one thing you learned from the previous video, it should be that talking about epsilons and deltas are horrible, awful things that no one ever wants to do, unless you're crazy, like me, in which case you might be the type of person who becomes a mathematical analyst and spends their entire life just looking at epsilons and deltas. Yes, that's literally what half of all mathematicians do with their lives, is just look at epsilons and deltas over and over again. And they enjoy it. And they think it's fun. And they do it as a hobby when they're not even working on it. I have problems. Anyway, some of these properties are going to be fairly straightforward. Let a and c in the real numbers be constants. Then we have two limits. The limit as x approaches c of a is equal to a, and the limit as x approaches c of x is equal to c. This says theorem, so that means I'm probably going to have to prove something here. All right, let's let epsilon be bigger than 0. And I'm going to skip the scratch work and just assume that the absolute value of x minus c is less than epsilon. That works. It will work. It will always work. Good enough for me. I guess it won't always work. It will always work for this particular problem. Saves us a little bit of time. All right, the absolute value of a minus a is equal to 0, which is less than epsilon. That's done. The absolute value of x minus c is less than epsilon by the assumption we made here. So that's done. That's it. Easy one. Next one is a little bit messier, but this is going to be a key idea that we're going to see quite a bit of. And you might recognize it from when we were talking about combining functions. We're looking at the limit of a linear combination, a times some function f plus b times some function g. And I'm claiming that that's the linear combination of the limits of each function on their own. This is a property called linearity. And things that have linearity are incredibly useful, and things that don't have linearity make you want to cry. All right, so we start off our proof. It's an epsilon delta proof, so we're going to let epsilon be bigger than 0. And in this case, I don't know anything about my function, so I'm not going to know anything about delta. But I do know a couple of things. I know that the limit of f of x is equal to L, and I know that the limit of g of x is equal to m. That means that there is a delta, so that f of x minus L is less than epsilon over 2a, because epsilon over 2a, I guess I didn't say that a is positive, so let's put that in absolute value, which is really just putting the a in absolute value. And likewise, I guess we should put the b here in absolute value because we didn't say that b was positive, we just said that they were constants. Now, the value of delta that satisfies the definition of limit for this, and the value of delta that satisfies the definition of limit for that, don't have to be the same thing. There's nothing in the definition of a limit that says it has to be the same thing. It just says there has to be one. But as we've discussed, if there is a value of delta, any smaller thing will be a value of delta that works as well. So if we figure out the value of delta that works for this, and we figure out the value of delta that works for this, we take the smaller of the two, and it's the value of delta that works here. All right, and again, why epsilon over 2a, why epsilon over 2b? Well, I think that's going to become pretty obvious, but again, you could go through and do the scratch work and figure out where the black magic came from. But why the a? Because there's an a there. Why the b? Because there's a b there. Why 2? Because you're adding two things together. So now we want to consider the absolute value of a times f of x plus b times g of x minus al plus bm. And going through and doing some algebra, I can regroup some things, get all of my a's together, get all of my b's together, factor out the a and the b. I'm going to do that all in one step just to fit more of this proof onto the screen at once. So we get a times f minus a times l, factor out the a, that's a times f of x minus l. And that's b times g of x minus m. Great. And now I'm going to hit the payoff for that triangle inequality that I talked about when we were talking about absolute value. The absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. And that's what we used here. We have two things added together inside the absolute value. If those two things have the same sign, then this is going to be equal if we split it up. If they have different signs, then what we ended up with is going to be bigger. And that's okay. Because I can now say that this is equal to absolute value of a times the absolute value of f of x minus L plus the absolute value of b times the absolute value of g of x minus m. And going back up to where our proof was, absolute value of f of x minus L, absolute value of g of x minus m, those are things we know stuff about. So this has to be strictly less than the absolute value of a times epsilon over 2 times the absolute value of a. And the absolute value of b times epsilon over 2 times the absolute value of b. Black magic. Absolute value of a and absolute value of b's cancel each other out. we end up with epsilon. And so let's go back to that limit that you've looked at before. The limit as x approaches 5 of 4 minus 3x. My instructions now say evaluate, because now I know stuff. By linearity property, the limit as x approaches 5 of 4 minus 3x is the same thing as the limit as x approaches 5 of 4 minus 3 times the limit as x approaches 5 of x. Then, by the evaluation, I'll call it eval theorem, the evaluation theorem, the first one we did. Well, the limit of a constant is that constant, and the limit of x is the value that you're looking for. So we get 4 minus 3 times 5, which is negative 11. And now that we have those theorems, this is all you have to do. You don't have to go through and prove everything in detail. When you don't have a theorem that applies, going back to the epsilons and deltas is important. It's something that you should know how to do, but you don't always need to. And so when there is a shortcut, we can take it. It helps if I write down the right theorem. All right, let's look at one more. If the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to M, then the limit as x approaches c of the product f of x times g of x is equal to L times M. All right. So let's let epsilon be bigger than 0. And because the limits on f and g are known, that means that there must be a delta bigger than 0, such that whenever absolute value of x minus c is less than delta, the absolute value of f of x minus L and the absolute value of g of x minus M are each less than some positive value. And here I'm going to choose the square root of epsilon as that positive value. Again, you could go through and do some scratch work to figure that out, I'm taking the black magic route, but notice that we have this L times M at the end. And so multiplying these things together might be something that's going to come up at some point. Seems reasonable. Square root of epsilon times square root of epsilon is epsilon, so that seems like something that should be helpful to us. All right, so let's consider absolute value of f of x g of x minus Lm. And it's not immediately obvious what we're going to want to do here, but it turns out that I can actually play a pretty nifty little trick. One of mathematicians' favorite tricks is to invent something that didn't exist. In this case, I'm going to invent plus L, I'm sorry, I'm doing this in the wrong order. I'm going to invent minus L times g of x and plus L times g of x. And I just realized that I used the wrong values for my epsilon. So I'm not going to end up with epsilon at the end, but that's okay. It'll still be kind of nifty when we're done. But from here, using the triangle inequality, this is less than or equal to the absolute value of f of x g of x minus L g of x plus the absolute value of L g of x minus Lm. We can factor out the common factor of g of x in the first one. And we can factor out the common factor of L in the second one. And notice that f of x minus L is less than root epsilon, and g of x minus M is less than root epsilon. And so we just need to figure this out. L is easy enough. I said I should have used epsilon, a root epsilon over L, but I wasn't paying enough attention when I was copying things down because I wanted to get this done quickly. But the g of x is not quite so obvious. So we can kind of mess around again using that trick of adding something that doesn't exist. This is the same thing as g of x minus m plus m. And we can split that up. This is going to be using the triangle inequality, less than g of x minus m times root epsilon plus absolute value of m times root epsilon. All right, so I don't end up with epsilon because I wasn't paying enough attention at the beginning. Right? But all this stuff is positive, right? Since epsilon is positive, root epsilon is positive, absolute value of m is positive, absolute value of L is positive, add it all together, it's positive. And we'll call it epsilon star instead of epsilon. And no matter what value we want for epsilon star, we can find a value of epsilon that we can plug in so that it all works out. That's good enough. It's not quite as satisfying a proof as I would have liked it to be, but it does work. Corollary to that, the limit as x approaches c of x raised to the n power is c to the n power. Right? I don't know if we've used a corollary yet. A corollary is a theorem that is ridiculously easy to prove based on a theorem that we just proved. So think about, using the theorem we just proved, how you could prove this corollary. All right, that will be your assignment. Think about how to use the theorem we just proved in order to prove this corollary. But before we do that, I just want to give you a couple of others. All right, so there are two other theorems which say that the limit as x approaches c of any function f of x to the n is equal to L to the n. The limit as x approaches c of f of x over g of x is equal to L over m. And surprisingly, that first theorem holds for any rational value of n, not just a real value of n, assuming that these things are all defined. Specifically here on the second one, we need to make sure that m is not 0. If m was 0, then we'd have some trouble. All right, so if I want to evaluate the limit as x approaches 1 of x squared plus 2x plus 5 over 9 times the square root of x. Well, using all of my evaluation rules, I can split up the quotient, I can split up the addition, I can put this inside the exponents and inside the root. Yes, inside the root, because a root is a rational exponent, right? Square root of x is x to the 1/2 power. This is going to be 1 squared plus 2 times 1 plus 5 over 9 times the square root of 1, which is 1 plus 2 plus 5, which is 8 over 9 times 1, which is 9. All right. There are some oddities that can and will show up. As I've mentioned, the whole goal on all of this is looking towards continuity. So we know that whenever we have a discontinuous function, bad things should happen to the limits. But whenever we don't have a discontinuous function, a polynomial function, a rational function when the denominator is not 0, and a radical function where the square root or whatever root is actually defined, everything works well, and limits are just a clunky way of saying evaluate the function. It was a long way to go to get there, but we have gotten there. In the next couple of videos, I'm going to be showing you how to use this to your advantage. And I'm going to be looking at the places where it's going to fall apart. But for right now, go back, that corollary that didn't quite fit on, there we go. Corollary, the limit as x approaches c of x to the n is equal to c to the n, based on the product rule that we had just proven. Prove this to yourself, see what you end up with, and I'll see you in the next video.